Okay, thank you for Professor Shi and the host of this seminar. My name is Zhuangzhuang Liu from um, the Department of Road Engineering at Chang'an University. The title today I will present is the influence of lower temperature and the lower current pressure on the Portland cement phase. Mainly, this presentation is a summary of our studies in the past 10 years. Especially part of this are summarized from my PhD thesis. I will introduce our researches from 6 parts. First one, I will introduce the reason and the background of our study, and then we will introduce some devices and the methods we use in the research. Third part, we will introduce the early frost damages in the cementitious composites, especially in the cement paste. This part will be related with the lower temperatures affect the cement paste at the earlier ages. The fourth part is the lower current pressures effects on the cement paste. This part we want to know how the lower current pressure will affect the cement paste. The next part, we did some calculation and modeling, use the kinetic and the thermodynamics methods, and then we will have some concludes. First one, the cold regions covers a large amount of the surface area of the Earth. Especially, there are two kinds of cold regions. The first one is those regions with high latitude, such as the North America and the Nordic countries and Russia. The second kind of cold region is high altitude regions, such as the Qinghai Tibet Plateau in China and some other mountains. For China, there is a large amount area that will be faced with the cold region and the cold climate, such as the Qinghai Tibet Plateau and some other province in the north and also in the west north. In this area, the transport infrastructures have been faced with the harsh climates. The harsh climates affect the materials behavior and the structures of infrastructure. Especially the wind event will attack the infrastructures not only on the transportation and also will broken or affect the materials and the structure, such as the bridges and the pavements. Considering the harsh climates, one important element, such as low temperature effects, are highly noticed and investigated. Such as we have the cold weather concreting method, and there are some standards, not only in China, but also in the USA and other countries. However, another thing, the lower air pressure is always less concerned in the infrastructure engineering. And even in some conditions, the lower air pressure is ignored in the concreting. Here, this figure is we summarized the relationship between the air pressure and the altitude. You can see the air pressure is directly reduced by the rising of the altitude. For the Qinghai Tibet Plateau, the average altitude is about 5,000 meters, and the related air pressure is about 0.5. Here we define the P0 as the relative air pressure to that of the sea level. This figure we have the relationship between the air pressure and the Qinghai Tibet Highway. Among the Qinghai Tibet Highway, we can see the air pressure among the Qinghai Tibet Highway falls in between 0.6 to 0.8 P0. So in this area with high altitude, we always know that the human being and the animals will have to be faced with the altitude reaction or the altitude sickness. Is it the cementitious materials or cementitious composites, such as the concrete and the paste or the mortar, will be also faced with the altitude sickness or altitude reaction? That is the question. So in our study, we do a lot of research focused on this topic and this question. Today, we want to introduce two parts. The first part is the frost damages caused by the lower or negative temperature. And the second part, we want to introduce some basic results or conclusions we got in our study, the lower current pressure effects on the cementitious composites. The material we used is the commercially used in China, the ordinary Portland cement produced in Shanxi province, and the chemicals to mix in the cement is we used the calcium chloride, sodium nitrite, and some other salt. All the cement are measured and can meet the required specifications in China. And the main devices for curing, we use two kinds of curing. The first one is the lower temperature curing. Before the mixing of the paste, we put the cement and the water in the in a fixed temperature that is similar or the same with the curing chamber. The second curing, we developed a system to produce the low air pressure. This is what we use in the laboratory to measure the paste. And also we have a bigger chamber to produce the lower air pressure so as we can curing the cement paste and the concrete samples. We also use the BT and the CT scanner to measure the material structures, especially for the microstructure and the macrostructure of the hardened concrete paste and the materials. We also use XRD, SEM, and TGA to determine the hydrates during the hydration. We also use the electrical resistivity tester produced by Hong Kong, especially the relative researcher is Li Zongjing. We also use the temp air to measure the heating and the hydration process during the hydration. The experiment or the research can be divided into 3 parts. We just stated in the introduction and the content initially. The first part, we want to know the effects on the cement paste by the lower temperatures, lower current temperatures. And the second part, we want to know the microstructures affected by the lower current pressure. And then we did some modeling based on the Gibbs free energy minimization criteria. We will introduce the current early frost damages we completed before. This is the basic knowledge that the strength during the lower temperature will be reduced. There's no more things want to be discussed here because it is a general result and the conclusion we can know before. But what I want to see is the flexural strength and the compressive strength is highly related with the hydration degree during the different current temperatures. So after that, we mixed and produced the cement paste at each temperature. So we want to know initially that at the earlier age, how the negative temperature affects the structure of the material and the performance of the cement paste. So based on the methods from Professor Li Zongjing and Professor Xiao, the cement hydration at early age can be described by 5 stages. That is dissolution stage, dynamic balancing stage, setting stage, hardening stage, and hardening decelerating stage. During the hydration, the setting stage is between the initial setting and the final setting. So we want to know the first frozen time. If the first frozen time located at the different stage, what will happen? So firstly, we measured our cement paste, use this machine, and we got the 5 stages, especially the 5 stage point based on the electrical resistivity during the hydration. And then we got 5 first frozen time located in these 5 stages. You can see from this picture. And then we put the cement paste under the standard occurring condition and at the relative time, we move the sample to the negative temperature, so that the frost damages will appear in the cement paste. This is the mechanical behaviors after frozen. We measure the strength. We can see the strength evolution under the strength still develop under the negative temperature, and the composites with the first frozen in the hardening decelerated stage show less reduction in the strength. Just the black point and the red point you can see is very nearly close. And also before the final setting, that is in the first 3 stages, in the dissolution stage, the dynamic balancing stage, and the setting stage, the strength is highly reduced, especially for this 4 and this 4 stage. And also there's a nearly no strength in the first 2 stage, is such as this point and this point, the dissolution stage and the dynamic balancing stage. If the first boson exists in the dissolution stage and the dynamic balancing stage, the structure and the material will be damaged totally. In the first 2 stages, we also measured the frozen temperature on the performance of the cement paste. In the first 2 stages, the negative temperature have similar destructiveness with others. After setting, lower frozen temperature brings greater strength reduction. You can see from here, from this blue part. And also the fracture strength is much more sensitive to the frozen temperatures and that have the compressive strength. What happened on the structure of the cement paste, especially on the hardened cement paste? We use the CT scanner to got the structure of the cement paste. This is the mechanism or the workflow of the 3-dimensional reconstruction with the CT scanner. This is the tomographic images of the samples, especially from the first 5 is from the 5 stages, and this is the control sample without frozen damage. We can see it is clear that the damages during the first 2 stages and the last 3 stages, the damage is less. This is the porosity of the cement paste during the we use the CT scanner. We can see that the porosity of cement paste is reduced with the delay of the first frozen time from the 30% to 3%, especially for the first frozen. If it is happened after the final setting, the porosities were nearly no changes, especially for the first, the last 2 points. And also, we got the 3D structure of the damages in used the CT scanner. We can see the delayed damages, the layered damages appears in the samples of frozen in the dissolution stages and the dynamic balancing stages is for these 2. And bubble damages happen after the final setting, such as from this one and this one. This is the control sample. And also for these stages is combined with the layered damage and bubble damages. The frozen damages in the 5th stage is similar with this control sample. So compared with the damages in the cement paste, we can have we summarize 4 types of frost damages in the early ages. The first one is before initial setting. We define it as type A. The damages is because is caused by the flow actuation of the paste. That is mean the cement paste is damaged by the freezing of the moisture in the cement. After final setting, we define it as type B damage. In this part, the expansion and the cracking appears in the cement, and the cement pastes are broken by the expansion of the moisture. And also in this part, we define, or we call it a type C damages. During the setting stage, the flow and expansion cracking damages happen together, and the strength will be reduced, and the performance is worse than the control. And after the final setting, we call it as the type D. In this part, the strength behavior and the performance is similar with that of the control sample, and also we found the structure of the sample is also similar with the control sample. So we thought, or we call it a type D. There's no difference, or the difference is very less than the control sample. And then we want to find some treatments for against the early frost damages, or to improve the performance at the early ages. So we use two methods. First one, we treat the sample by pre-curing. We put the sample under the standard curing condition, and then cure it at 5 degree. This is lower than the standard condition. The pre-treated in our study include pre-curing and the chemical modification. So this is the pre-curing effective and the treatment on the mechanical properties of the cement paste. We can see the longer pre-curing treatment will cause the reduction of the mechanical performance. This is not as expected as we carried out the experiment before. We thought higher temperature curing will bring higher strength, but in our experiment, we found that higher curing temperature bring lower mechanical performance. We also use the mechanical to treat or to modify the the behavior of the cement at the early ages. We can see both the flexural strength and the compressive strength were reduced by the chemical accelerators expected for the calcium chloride in this. This is also out of our expected. We always know that the salt and the chemicals, most of the chemicals can accelerate the hydration and the strength development of the cement and concrete. However, in this study, we also get the similar result as the pre-curing treatment. So we can conclude for this result, it should be very cautious to use chemical accelerators together, or use the pre-curing in cold regions, because in cold seasons, the improvement might be offset with each other, or unclear strength development will be appear. We also measured the heat flow and the heat release during the cement hydration. We can see the peak and the values of the heat release is different and changed by the chemicals used in the cement mixtures. What I want to see is you can see here the calcium chloride have the fast cement hydration and the first one to achieve the peak. And also we want to know what happened during the cement hydration and the chemicals, how the chemicals influence or affect the cement paste, especially on the strength development. We can see this curve is the initial setting and the final setting time, and this is the peak time during the cement hydration. Use this figure, and this is the heat cumulative heat during the cement hydration we use from this figure. So we can see that the peak time and the initial time, the curve and the trend is similar. And also we compared the initial setting and the final setting time in this figure and with the strength development during the hydration. We cannot find a clear relationship between the initial setting and the final setting with the strength of the cement paste. However, if we compare the difference between the initial setting and the final setting, this is the delta time between the initial setting and the final setting. It will be similar with the strength development. So we can see the longer setting difference will be beneficial to the strength development, especially at the lower temperature. We have some discussion and some comments on this phenomenon because the inner cracking or micro inner cracking will be caused by the preheating or the chemical accelerators are the main reason to reduce the mechanical behavior or the strength during the early ages, and the micro inner cracking happens during the initial setting and the final setting. This is what we all know before, and the chemical should be evaluated by very carefully according to the environmental conditions. We will introduce some conclusion and what we learned before at the lower current pressure effect, especially on the microstructure. This is the degree hydration during the lower pressure. We can see the this is the we carried out the study under 0.2, 0.5, 0.8, and 0.9, and the P0. So we can see that during the first day of the hydration, the lower current pressure affects the hydration degree, but at the later or up to 3 days later, the current pressure have less effect on the degree of hydration. Why we choose the 0.8 and 0.5? Because we introduced before in the Qinghai Tibet Highway, we are facing these problems. So we choose this section to measure the low current pressure effect. We use XRD to detect the hydrates during the hydration. We can see that there's no differences between the cement hydrates and under the lower current pressure and the general or the standard current pressure. There's no significant differences between them. However, in the TGA measurement, we have find some differences for such in this part. It means the water absorption in the CSH or the AFM or some other hydrates is different, maybe because the lower current pressure or the hydrate structures, the high structures of the hydrate. So this is what we got, the enthalpy and the mass fractions during the TGA. We can also see that the very slight differences in the water fractions from this part, but the curve here is different, and also we can see the Portland diet is also different, especially is reduced by the lower air current pressure. We also calculate the microstructures, especially for the pores in the cement paste. We can see the peak in this figure can be divided into 3 groups. The first one is about 3 to 20 nanometer, and the 20 to 50 nanometer, and the 50 to 100 nanometer. So we define the first group as the micropores. The second group is the mesopores, and the last group is the micropores. The micropores is always produced by the inter layer spaces. So we can see the a slight reduction of the pore volumes is observed from the interlayer spaces with the decreased current pressure from P0 to 0.2 P0. And also the lower current pressures causes an increase not only in the micropores but also in the mesopores and the micropores. That means the durability of the cement composites or the cement concrete in this condition will be worse, or we have to put more conditions in the service life. We also did some modeling. First, we did some modeling to calculate the cement hydration under the lower temperatures and the lower current pressure. The developed hydration degree is closely related with the current temperatures, and in the modeling we considered the current temperature, the water cement ratio, and the specific surface area, and also we also conclude the lower current pressure. This is some data and the results we got in the simulation and modeling. We also use the GIMS to do some thermodynamic modeling under the lower temperature and the low pressure. The database we use is the cement data developed by the EMPA and University of Aberdeen, and also PSI and Friends minimization are also used in our research. We can see this point and this point are what we got from the experiment, and these are calculated. It proves that our calculation and the experiment data is good, and also we got the hydrates during the lower cooling pressure and the lower cooling temperature. Based on our study, we summarize the temperature ranges and the effects at the lower temperature. It can be divided into 3 levels. The first level is if the temperature is negative, that means is lower than 0 degree. The damages is irrecoverable. If the temperature is located on between 0 to 10 degree, that means the hydrates maybe in the thermodynamically will be changes dynamic. So we have to put more phases at the phase changes during this temperature, and also the durability will be reduced in this temperature. If the temperature is low, is between 10 to 25 degree, we call it as insignificant effects. That means the hydrates is stable, and also the hydration is similar than that with the standard current conditions. So we also did some modeling and experiments to compare or to find out why the lower occurring temperature, occurring air pressure will affect the microstructure, because we have known that the hydration is similar with the standard condition. We found that the calculated water cement ratio were varied from 2.43 to 0.52 up to the 14 days of the curing, because we the moisture evaporation occurred during the lower air pressure curing. That is the main reason we found before, and we also published the detailed discussion in our paper. And also we do some calculation between the mass fraction of Portlandite in the experiment and in the modeling, and also did some lower compression effects on the pores in the hardened cement pastes. Conclusions: based on our study, we know that the altitude reaction or the thickness for the cementitious composites, including the lower temperature effect and the lower pressure effect. And also there are 4 typical frost damages at early ages, and the lower air pressure have slight effects on the hydrates, but however, it has a significant influence on the microstructure of the hardened matrix. The main reason is believed to be the moisture evaporation. And also the lower temperature could be divided into 3 sections based on the thermodynamic calculation and the experiments. In kinetic, the lower air pressure has slight effects on the hydration, and the hydration rate, which could be ignored in the real applications or in engineering. At all ages, temperature control and the materials design should be carefully considered to prove or to make sure the performance during the service life. This is our publications during this introduction, and also Dr. Low from China University and now is working in Norwegian University of Science and Technology. PhD candidate Li Ling is my student, and also Dr. Diego is from NTNU. It's a former postdoc. And all the experiments and the modeling work are completed at China University, and also our work and the study are funded by the NSFC. That's all. Thank you.
All right, thank you so much, Dr. Liu. Actually, the session chair, Jialo, he had to leave because the conference room staff needs to clean up the conference room. So I'll just, as a backup, I'll just help wrap up this session. So thank you for the presentation. If anyone has any questions, please feel free to use the chat or just unmute yourself and ask directly.
Thank you. Any questions?
And also I see the email address is there. So that will be another way to reach out to Dr. Liu as well.
Yeah. If you have some question, you can also send your question via the email, and I will answer that.
Let me check the chat. So actually, I'm curious because my background is not in civil engineering. I'm a computer scientist. I'm here just, help. I'm wondering, like in your field, like once you develop this technology, all these models, and do you actually work with industry to apply this, or is that like an ongoing work?
Yes. 2 works are ongoing. First one is we want to use the method and the control strategy in our study to the real engineering. What we are working now is to improve the concrete in the Tianshan, such as the Duku Gonglu. Duku Highway is the very famous highway in China.
Yeah.
And also the second work we are doing is we did a lot of calculation, including the thermodynamic calculation and the kinetic calculation. Yeah, we want to use these equations and to include in some engineering, how to say, in the temperature control in the concreting procedure.
Yeah.
We want to develop some control system to use the solar energies and to compare with the to support the how to say, because we have to keep the heat to warm the concrete during the cold conditions. So we are using this method to combine the solar energies to support the hydration and the hardening of the concrete.
It's very interesting. Thank you, Dr. Liu. Let's see if we have any more questions from the audience.
Okay, thank you.
Okay. All right. So we're 5 minutes past the scheduled time. I guess we can end the session. Thank you for all the speakers, and thanks everyone for attending. Thank you very much.